I wanted to do some more examples with these homogeneous systems to show different situations that can arise. I did a couple examples last time. Let me do a few more this time, just to see what kind of things that can happen. So let's start with a system of 2 by 2. I have negative 6, 2, negative 3, 1, and that's times x arrow. First thing we do is compute the eigenvalues. And that's setting this determinant equal to 0, negative 6 minus lambda, 2, negative 3, 1 minus lambda. That determinant set equal to 0. Go ahead and solve by cross multiplying. So I'll have negative 6 minus lambda times 1 minus lambda plus 6 equals 0. Let me multiply this out. I'll have negative 6 plus 6 lambda minus lambda plus lambda squared plus 6. Let me go ahead and organize some things here. Lambda squared, looks like I have plus 5 lambda, and the 6's cancel. So I have lambda times lambda plus 5 is equal to 0. Or in other words, lambda equals 0 and lambda equals negative 5. So remember, from these two things, you're supposed to get our eigenvectors. Once we have distinct eigenvalues like this, we know that our answer is going to look like, it'll look like C1. I'll have some sort of an eigenvector, but it'll be e to the 0t because of the 0 eigenvalue. And then I'll have plus C2, another eigenvector, e to the negative 5t. So that's what our solution will look like once we go and find out what K1 and K2 are. Let me start with lambda equals 0. So it really doesn't do anything. We have our original matrix. And you can wipe out one of these rows. Say if I take 2 times the second row, or negative 2 times the second row and add it to the first, I'm able to wipe out a whole row. Now remember, if you convert this to equations, we have negative 3x plus y equals 0. And so you'll have y equals 3x. So when you create your eigenvector, try to make it as simple as possible. For example, if I let x equal 1, notice you don't want to let x equal 0 because you'll get 0 for an eigenvector, and we don't allow that. So let x equals 1, and you'll get y equals 3. So there's one eigenvector. And the other one was lambda equals negative 5. So this time we are looking at negative 6 minus negative 5, 2, negative 3, 1 minus negative 5. Let me simplify it a little bit. Here on the top I'll get negative 1, 2, and on the bottom I will get negative 3, 6. And the same kind of thing happens. I can use the first row to wipe out the third row and wind up with just this. And then this becomes negative x plus 2y equals 0, or 2y equals x. And this time when I do my vector, I find it more convenient to allow y to equal 1 this time. That way x is equal to 2. I'll avoid fractions as much as possible like anyone else will. And that's my second eigenvector. So my answer we had 1, 3. That was attached to e to the 0t. And then we've got C2, 2, 1 was attached to e to the negative 5t. I could simplify this just a little bit. My answer will look like C1, 1, 3, plus C2, 2, 1, e to the negative 5t. For my next example, let me do a 3 by 3 system. So mine is 2, negative 7, 0, 5, 10, 4, 0, 5, 2. And as before, let me first do the eigenvalues. So I'll have 2 minus lambda. The only entries that have a minus lambda are the diagonal entries. And we set that determinant equal to 0. For the computation of this determinant, I've done it before, but I'll do it again. You can go across a row or you can go down a column. Any row you want, any column you want. I would typically choose the row or column that has the most zeros so that I minimize how much work I have to do. With that being said, I'm going to start and go along the first column. So I'll have 2 minus lambda times the determinant. Remember how this works. I get rid of the row that it's in and the column that's in, and then what's left over is a little mini matrix. 10 minus lambda, 4, 5, 2 minus lambda. And then I move on to the next item in the column. Of course, you can go across the row too, it's no big deal. So let me go ahead and erase these lines. Now I'm going to go down and move on to 5. You also have to change the sign as you go. So now I will get rid of the row that 5 is in and the column that it's in. And I'll have negative 7, 0, 5, 2 minus lambda. Now for the third one, plus, I would be plus again. I have a 0. That means I don't even have to worry about this because 0 times whatever is still going to be 0. So this is as far as I need to go here. And now let me go ahead and multiply everything out. So I have my 2 minus lambda. The determinant in here, I'll get 10 minus lambda times 2 minus lambda. And then subtract the other way, minus 20. I have minus 5 times negative 7 times 2 minus lambda. And then the other way, minus 5 times 0 is just 0, so I don't have to worry about that. I'm going to simplify in here a little bit. So I'll get, inside of here, I'll get 20 minus 10 lambda minus 2 lambda minus 12 lambda plus lambda squared. And then I have minus 20. Well, that's nice. On the other one, there's not much here to do except I have 35 times 2 minus lambda. Let me cancel these 20s while I'm at it. Now this was really nice. You notice you have a 2 minus lambda attached to both pieces, so I'm going to factor it out. What will be left then is my lambda squared minus 12 lambda plus 35. That'll equal 0. I can factor this stuff in there. I'll get 2 minus lambda times, looks like lambda minus 5 times lambda minus 7. So my eigenvalues will be lambda equals 2, 5, and 7. So I'll start with my first lambda will be 2. And then let's take a look at the matrix. I had 2 minus 2, negative 7, 0, 5, 10 minus 2, 4, 0, 5, 2 minus 2. Let's clean up a little bit before I do any simplifying. I have 0, negative 7, 0. In the last line, I get 0, 5, 0. And in the middle line, I'll get 5, 8, 4. I do not know why I put that y there. That should be a 0. Well, notice here's what we have as far as our equations. I don't care about the first and last one so much. The first equation tells me that negative 7y equals 0, and the middle equation tells me that 5x plus 8y plus 4z equals 0. Notice that negative 7y equals 0 forces y to equal 0, so this equation down here becomes 5x plus 4z equals 0. And then probably, there's a lot of ways you can do this, but I think what I'll do is rewrite this as 5/4 x. I'll do negative 5/4 x equals z. So I simply subtracted 4z and divided by the negative 4. That way, when I construct my eigenvector, it's going to be 3. It's going to have 3 entries. It'll be 3 rows. I'm going to choose x to try to avoid fractions. So if I let x be equal to 4, z will equal negative 5, and we already found that y was equal to 0. Now what were my other eigenvalues? 5 and 7. Let's move on to lambda 2 equals 5. This time my matrix will be 2 minus 5, negative 7, 0, 5, 10 minus 5, 4, 0, 5, 2 minus 5. Let me simplify. I'll get negative 3, negative 7, 0. Then I'll get 5, 5, 4. And then I'll have 0, 5, negative 3. What I'm going to do is what they call elementary row operations and try to clean this up a little bit, because right now, while I see that x and y are connected and so are y or z, this middle one, I'm not exactly sure what's going on there. Let me clean up a little bit here. What I'll do is I will multiply the first row by 5 and the second row by 3. The reason I'm doing that is so that they're compatible for adding, and I'll be able to cancel out the x portion. So when I do this, I'll have negative 15, negative 35, 0, 0, 0, 0. Then I'll have 15, 15, 12, 0, 5, negative 3. Now what I'll do is I will add row 1 to row 2. And I write that as r sub 1 plus r sub 2. So I have negative 15, negative 35, 0, 0, 0, 0. And so I have 0 here. Here I'll have negative 20 for my middle term there. And I will not affect the 12. And then I have 0, 5, negative 3. Now you can see what's going to happen next. I can take the third row, I can take 4 times the third row and wipe out the second row. So when I do that, I will zero it out completely. This should tell you without any doubt that I have 2 linearly independent equations. Now on the first row, I could divide the first row by -5 and end up with, if I divide the first row by -5, I'll end up with 3, 7, 0, 0 down the last column, 0 in the middle row, 0, 5, -3. So this gives me two equations. On the first row, I have 3x plus 7y equals 0. And on the last row, I have 5y minus 3z equals 0. What I can do is write both x and z in terms of y. So I can start and get x equals -7/3 y, and at the same time, I can do z is 5/3 y is equal to z. So the reason why I'm doing it this way is because, remember, I'm trying to pick these things to be as easy as possible, avoiding fractions if I can. So it seems reasonable to me for my second eigenvector that if I chose y to be 3, then neither x nor z would be fractions. So if y is equal to 3, x is equal to -7, and then z is equal to 5. And then what was our last eigenvalue? Was, I believe, 7. Yes, our last eigenvalue was 7. So lambda equals 7. We have 2 minus 7, -7, 0, 5, 10 minus 7, 4, 0, 5, 2 minus 7. I'll have -5, 5, 0 for my first column. Then I'll have -7, 3, 5 for my second column. And then my last column, I'll have 0, 4, -5. Here, I'm in a similar situation as before. You can see what happens here. If I use this first row to wipe out the 5 down here, I'll get -4 and 4, and then I'll be able to wipe out the third row or the second row, whatever I want. The point I'm making is this. I'm going to be left with two equations. -5x minus 7y equals 0. The middle one will get wiped out should I desire to do it, but I don't. I'll move on to the last row. 5y minus 5z equals 0. So then let me go ahead. I see y is involved in both of them, so I will solve each in terms of y. So I have -5x equals 7y, and I will divide by the -5, and I'll get x equals -7/5 y. On the other hand, this is pretty easy. 5y equals 5z means that y simply equals z. So I just need to pick a y that's a good, easy number to use. And I see that y equals 5 might be a good idea. That'll force z to also equal 5, but x will be -7. And so we have our answer. X is equal to C1. My first eigenvector was 4, 0, -5. This is, of course, the eigenvalue associated with this first eigenvector was 2, e to the 2t, plus C2. My next eigenvector was -7, 3, 5. That was attached to the eigenvalue 5. And then finally, my third constant is multiplied to this eigenvector here, -7, 5, 5. And then I have e to the 7t. For my next example, let's do a 2 by 2, 12, -9, 4, 0. And as before, I'll figure out my eigenvalues first. 12 minus lambda, -9, 4, 0 minus lambda is just negative lambda. These kind of determinants are easy. I have 12 minus lambda times negative lambda. The other way would be plus 36. And so when I multiply this through, I'm going to get lambda squared minus 12 lambda. And so here, if I factor it, it looks like I get lambda minus 6 times lambda minus 6. So I get lambda equals 6 twice. 6 is a repeated eigenvalue. Now we'll know what to do next depending on how many eigenvectors this gives me. It's possible that this will give me only one eigenvector, or I may actually get two out of the deal. Let me show you how that can even possibly happen. So when lambda equals 6, let's take a look at our matrix. We will have 12 minus 6, negative 9, 4, negative 6. And let's see what happens here. I get 6, negative 9, 4, negative 6. Now, if I take negative 1.5 times the third row and add it to the second row, I'll be able to zero, and add it to the first row, I'll be able to zero out the first row. Just to probably simplify things as much as possible. Well, I won't go any further here. I have 4x minus 6y equals 0. 4x equals 6y. Or solving for one or the other, I think I'll say 4/6 x equals y. That's the same as 2/3. This is 2/3 x equals y. So if x equals 3, y will equal 2. So I have exactly one eigenvector, and it's 3, 2. That's not enough. We have to have a second solution. Right now, I have only one solution. Let's call it x1. That'll be, I don't need this, well, I'll put it there anyways. But the x1 is not, the c1's not part of the x1. And the eigenvalue was 6t. Now, it would be nice if our entire solution were c1, 3, 2, e to the 6t. Whenever we have repeated roots, we just simply did this. T, e to the 6t, and that would be our solution since we have a repeat. That's how we work these things. Unfortunately, this is not true. It is not true. So how do we manufacture another solution? So let me come back to this problem in a little bit. So to manufacture a second solution. This is in the case of eigenvalues that give you too few eigenvectors to work with. To get a second solution, this is what we do. This comes into play a little bit. Well, what you do is you let x2 equal k, and we'll call it k. Well, it's just k. There's only one. I don't have to call it k1. But my next one then will be k t e to the 6t. So there it does happen. It pops up in there. But this has to do with the number of operations and combinations of operations and things like that for all the possibilities that you have to consider for something like this to happen. This is how we generate a second solution, is in this format. Now we have the general format of our equation looks like this. I mean to take this and substitute it into here and here. Into here is not a problem. First, let me take the derivative of x2. Now, as I mentioned before, the k is nothing but constant coefficients, so they're not involved in any kind of derivatives, but this stuff is. So, as typical, I'll take the derivative of t as 1, and then I'll leave that part alone, and I'll get 6e to the 6t. Then the second one, that'll give me 6e to the 6t. And also over here, I'll just plug it right in. So let me go ahead and throw this stuff in here. So in this equation, I'll put this stuff on the left. E to the 6t plus 6te to the 6t plus 6p e to the 6t. And the right-hand side, I'll get my a, and I'll go ahead and throw in this stuff here. Now, since you're constructing this just like anything else, you can have some convenience here. What you might do is allow t to equal 0. You can pick whatever values you want. You're just trying to manufacture a solution. If I let t equal 0, I will get a k, and then I will get e to the 0 plus 0. That'll be a 1 here and a 0 here, plus 6 p arrow times e to the 0 equals a times k arrow times 0 plus p e to the 0. Well, this simplifies quite a bit. Here I'm just going to get a k. Here I'll get 6 p arrow. On the right hand side, I will get a times that. And then what I want to do then is, let me take the 6p to the other side. That equals ap minus 6p. Remember, this sort of factors, but you have to do a minus 6i. So I can use this to manufacture my other p. In fact, in general, you'll have to solve an equation like this. Remember, 6 was the eigenvalue. And in our solution, to get a second solution here, we already know what k is. It's just trying to figure out what p is. So let me go ahead and do this. The k, where was our k? Our k was 3, 2. So let me put it in. A minus 6i, we've done this 100 times. That'll be 12 minus 6, negative 9, 4, negative 6. And for now, I'm just going to call P, P1, P2. Those will be the entries of that vector. And I'm trying to figure out what P1 and P2 are. Matrix multiplicate, well, not quite yet. I have 6, negative 9, 4, negative 6, P1, P2, 3, 2 equals. Let me go ahead and do my multiplication. Remember, you do 6 times P1 minus 9 times P2. On the second part, you get 4P1 minus 6P2. And so you do get a system of equations. You get 6P1 minus 9P2 equals 3. And then I got 4P1 minus 6P2 equals 2. This is no different than the previous problems, because once again I could take negative 1.5 times the second row, add it to the first, and zero it out. So either one of these will be acceptable. I'll use the second row for convenience because I'm going to divide it by 2. Now, as before, you can allow anything you want here. I'm just trying to figure out what a P1 and P2 are so I can fill out my P. You could, if you want to. In this case, you can permit one of the P's to equal 0 because you're not going to get a 0 vector. You have something's got to equal this 1. So let's just suppose I let my second entry equal 0. Then my first entry, if this zeroes out, I have 2p1 equals 1. I'll get a 1/2 for my first entry. And I'm all done. So my second solution, remember that was k arrow times te to the 6t plus pe to the 6t. Or if you really want to make it look like it's a repeated kind of a thing, you could always do k t plus p e to the 6t. Our solution then, the entire solution, we already had but then our second constant will be attached to this stuff. K was 3, 2 times t plus my p was 1/2 0 e to the 6t. So you can see it's kind of like our regular repeated zeros, except not quite. There's a little bit extra going on here. Here's another 3x3 that we're going to give a shot. As you always do, the very first thing you want to do is try to figure out them eigenvalues. So I'll have 3 minus lambda, 2, 4, 2, negative lambda, 2, 4, 2, 3 minus lambda. Now, unfortunately here, nothing zeroes out. There's no zeros or anything like that. I just got to pick a row or a column just for the purposes of being a little different than I was before. I think I'll use the first, I'll go across the first row, and then you'll still do the same stuff. Cancel the first row and the first column. You have 3 minus lambda. That is times what's ever left. Negative lambda, 2, 2, 3 minus lambda. Now as you move across the row, let me erase this line and this line. As you move across the row, you do the same thing you did before. Change the sign. And then let's see what's left over. 2, 2, 4, 3 minus lambda. And then I'll move on to the third item. This time you change the sign again. It'll now be plus again. I have 2, negative lambda, 4, 2. This whole thing has to equal 0. So let's see what we get here. 3 minus lambda. Let's see, I have negative lambda times 3 minus lambda minus 4. And then on the second piece I have negative 2. And then I have 2 times 3 minus lambda minus 8. And then I have plus 4. 2 times 2 will be 4. Negative 4 times negative lambda will be plus 4 lambda. Now what I like to do is, just in case I'm able to factor it, to prepare myself for the purposes of factoring, I'm going to try to leave everything in factored form just to see what I can do with it. Let me multiply my lambda through here. I'll get negative 3 lambda plus lambda squared. For the second piece, I'll get 6 minus 2 lambda minus 8. 6 minus 2 lambda, negative 2 lambda minus 2. Here, what I'm going to do is factor a 4 out of this. Let's see what happens in my next line. Here, I can factor this piece, and I will get lambda minus 4 times lambda plus 1. Here, I can factor out a negative 2, and that will leave me with a lambda plus 1. And then finally, I have a 16 times 1 plus lambda. So my technique did work out here. I don't guarantee it on every problem, but sometimes it does. Notice that you have a 1 plus lambda attached to everything. So I'm going to factor it out of everything. Lambda plus 1. What will be left is a 3 minus lambda times lambda minus 4 plus 4 plus 16. So I'll have lambda plus 1. Here, let me multiply this out before trying to factor. I'll get 3 lambda minus 12 minus lambda squared plus 4 lambda plus 20. All right, let's see what we have in here. Then I have a negative lambda squared plus 7 lambda plus 8. That equals 0. For me, factoring something like this is sort of weird to have a negative in there. So if I multiply everything by a negative, negative 0, of course, will stay 0. I'll just put the negative through here. I'll get lambda squared minus 7 lambda minus 8. So this part here, I can write it as lambda minus 8 times lambda plus 1. And then here we have a situation where I have a repeated eigenvalue again. So what do we get? I get for lambda, I'll get negative 1, and 8. Plug those in and see what happens with the matrix. So when lambda equals negative 1, I'll have 3 minus negative 1, 2, 4, 2, negative 1, 2, 4, 2, 3 minus negative 1. Let's see what this equals. I'll get 4, 2, 4, 0, 2, 1, 2, 0, 4, 2, 4, 0. Let me put my line to indicate it's an augmented matrix. Now if you see, all 3 of these are multiples of the other 2. So what I can do is I can use the second row to wipe out both the first and the third row. I can take negative 2 R2 plus R1, negative 2 R2 plus R3, and that'll wipe out the first and third rows. What I'm getting at is after doing that stuff, you'll have a matrix like this. You don't even have to do that to see where I'm going here. Now this is interesting. This is a little bit different before. We have 2x plus y plus 2z equals 0. Now, from this one equation, since I don't have 2 equations where I have something common, I can actually create 2 eigenvectors out of here. For example, I could start with x equals 0, and you'll have y plus 2z equals 0, y equals negative 2z. So this gives me the eigenvector. Have I done an eigenvector? No, I have not. So we'll call it k1. Since x was 0, Here, I could let z equal 1, and then y would be negative 2. And then I can go and say z would equal 0. The reason why I'm doing that is because that's the easiest stuff in my mind to let equal to 0. You could have let y equal 0. You could let x be 1 and y be 5. It doesn't really matter. I'm just trying to choose the easiest numbers. If I do this, I'll have 2x plus y equals 0, or 2x, negative 2x equals y. In this situation then, for my next eigenvector, here I'll set the z equal to 0, and then if y, it's a little bit different here. Let me see what we have. When x equals 1, y will equal negative 2. And so I've got two eigenvectors that way. That's good. So I don't have a situation like in the previous problem. These two eigenvectors, these two different eigenvectors, will lead to two different solutions. And then we have a lambda equals 8 is my third eigenvalue. And my matrix then, 3 minus 8, 2, 4, 2, negative 8, 2, 4, 2, 3 minus 8. When I simplify, I get negative 5, 2, 4, 0, 2, negative 8, 2, 0, 4, 2, negative 5, 0. Now you can see there's some similarities in the first row and the third row, but not quite exactly the same. And it's not clear to me that I can just wipe everything out right off the bat. What I'm going to do is I'm going to divide the second row by 2. So I'll call it 1/2 R2. And then I'm not going to do anything to the first row just yet. Second row will be 1, negative 4, 1. And then I'll have 4, 2, negative 5. This is what I'm going to start working. I'm going to wipe out the first entry by multiplying the second row by 5 and adding it to the first row. So if I do 5R2 plus R1, I'll be able to wipe out the x portion. I'll get negative 20 plus 2 will be 18. 5 plus 4 will be 9. Next, I'll leave that one alone. I'm going to wipe out the first entry in the third row. In order to do that, I'll do negative 4 times R2 plus R3. So I do that. Negative 4 plus 4 will be 0. Negative 4 times negative 4 is 16 plus 2 will be 18. And then negative 4 plus negative 5, negative 4 plus negative 5 will be negative 9. Before I continue, let me fix one error that I have right there. Now, if I add rows 1 and 3, so if I go row 1 plus row 3, or vice versa, I'll get 0, negative 18, 9, 0, 0, negative 4, 1, 0, 0, 0, 0, 0, and then I forgot the 1. Then here, I'm going to divide the first row, or I'm going to multiply the first row by negative 1/2. And I'll get 0, negative 1/9. I'll get 0, 2, negative 1, 0, 0, negative 4, 1, 0, 0, 0, 0, 0, and Now to finish off the deal, I think what I'll do is add row 1 to row 2. What I'm trying to do is make this very easy to see what's going on here. 0, 2, negative 1, 0 down the last column. When I do that, 2 minus negative 4 will be negative 2, but the 1's will cancel. This makes it really easy for me to see that once again y is kind of the linchpin to both of these rows. In the first row I have 2y minus z equals 0, or 2y equals z. In the second row I have x minus 2y equals 0, or x equals 2y. So it seems reasonable for me to allow y to equal 1 and see what happens with x and z. When y is 1, x will be 2. When y is 1, z will be 2. And I have my 3 distinct eigenvectors. My solution then may sort of surprise you. You would think that there's a t, e to the something in here, but there's not. These two here will each be attached to, of course, different constants, but C1, let's go back and get my K1, 0, negative 2, 1, and that was attached to negative 1 for the eigenvalue. Then I have plus C2, the other manufactured eigenvector, was 1, negative 2, 0. And that was also attached to negative 1. Finally, this last one was attached to the eigenvalue 8. And so there is our solution.